and our advisor Ranjit Jala from UC San Diego. So today I'm going to be talking about how we can create an extensible static analysis for a modern scripting language. And the language we're going to focus on is TypeScript. TypeScript was created by Microsoft and is now used widely. It looks a lot like JavaScript and actually compiles down to JavaScript, but also more interest for the programming languages community. For example, we have oriented and has a rather sophisticated optional. When we talk about static analysis, we mean that we want to create a tool specification that we have, and when these type time overhead. So what I'm going to be talking about is completely is that we don't want to be limited in a fixed set of time. For example, be able to specify the invariants or general value based. The minimum element of an array. One applying function f at each iteration and uses an index that calls to reduce with the. So let's assume that the verification goal here is to the step function. An array bounds analysis would require A, and so we effectively have a constraint between two values. This constraint becomes one between a value, A, and a step to the reduce function. And so the constraint now carries over. F. We need to somehow check that the constraint is actually having here is that in order to check an array access, we need to solve this in our tool is through refinement types. Refinement type is a base type of the set that we're describing. The formula P is true. For example, so how can we use this now to type the apply a TypeScript type. We'll express the fact that the function f accepts. Not doing really well at capturing the intuition. So to do that, we can use a refinement type, third parameter with a valid index that we saw earlier. So in a nutshell, our contribution is to design challenges. In particular, we had to figure out a way to deal. And we wanted to keep the annotation overhead as small as possible. New. And I'm going to focus on some of them for the. Let's get back to the original example of reduce. A while loop. Now, in order see that I gets assigned 0, so at that point, I. Then throughout the loop, we have multiple. And then right before the loop body ends, it gets expected to be equal to the length of a single precise type of the that we can assign to I. So far, in a single type, different versions of I. So now the different colors with versions that use script, and now we don't need the colors anymore. Each version of I now has a single precise type, but this is a transformation from the compiler's literature called static single assignment. Have computed for the program. As a reminder, an assignment of the form x. So using that intuition, then the first 0 and I1. Then we don't really have an explicit assignment to I induction variable in this case. And so I2 is the phi variable according to the SSA literature. And so it gathers values from I1 and I3. And so we get a constraint between the type of I1 and I2 and the type of I3 and I2. And notice here that we have encoded the loop condition as a precondition for this constraint. And this encodes path sensitivity. Similarly, we create constraints for the assignment to I3. And finally, a constraint to encode the safe array access. So now we gather a bunch of constraints, and we can use the original types that we assigned to I1 through I4 in the loop condition and substitute those in these constraints and end up with an expanded version of these constraints. And as is typical with refinement type systems, we convert these to logic and implications that can then be solved via an SMT solver. I'm not going to go into the details as to how this is done or how we can actually infer the types for I1 through I4, 3, since these are usually found in existing refinement type literature. So moving forward, let's see how our system tracks and handles mutable state. Let's take a closer look to the reduce example again. And let's see what happens with, let's try to answer the question intuitively of why the axis 8 at I is safe. So one thing is that the index that we're using is initialized to 0, then it's bounded by the length of the array A, and it only increments. But also there's a very crucial condition that says that the length of array A does not mutate in the loop. To see how this could break things, let's assume that we're actually trying to remove an element inside the loop right before the axis by using the pop method. This method silently updates the length of A. And so the check that we did at the loop condition now becomes stale, and the access to the ith element is potentially unsafe. So the problem that we're facing here is that stale checks break value reasoning. And the idea to tackle this problem is to extend the type system so that we can enforce some immutability guarantees. Fortunately, there's a long line of work in object and reference immutability, ranging from relatively simple extensions to the basic type systems to more sophisticated rely guarantee protocols. The method that we decided to use in our tool is the one called mutability generic Java, and the reason is that it's a relatively simple extension to the type system, and then by using that, the refinement analysis can operate using the guarantees set forward from that. So let's see how this works. So I've updated the signature for the reduce function so that instead of saying array of A, now we say array of immutable A, which means that the mutability is now part of the type parameter list. So the mutability modifiers themselves form a type hierarchy, and each modifier denotes what modifying permissions the current or other references may have on the referenced object. What is crucial in our case is that we only allow immutable portions in refinement types. So this A there needs to actually be an immutable array. So let's see how this can prevent the error from earlier. We also update our array spec so that pop can only be applied to mutable receivers now. And so at this point, at the call to pop, we're going to see an error flagged because the array A is immutable. So moving on, I'm going to be talking briefly about overloading, and in particular, special kind of overloading that we call value-based overloading. And here, the function can reflect upon and behave according to the types of its arguments. And to make this clear, let's assume that we have a wrapper around the reduce function that we saw earlier. This function calls reduce with either, this function can be called with either 2 or 3 arguments. In the case that it is called with 3 arguments, we have the first behavior. And in this case, x is expected to be of type B, as we can see also in the signature in the bottom. However, there's also another behavior that we expect, which is when it's called with 2 arguments. And in this case, x is considered to be undefined, as we can also see in the, and we can also see the signature on the first line. So what is it that makes checking these kind of functions challenging, and how common are they? To answer the first question, let's see what we did so far in our technique. So we've combined a type analysis that is based on the basic types with an analysis based on the values, which is what the refinements are there for. However, refinements use the invariants that were established earlier by base types. For example, if we want to track the length of the array A, this requires us to know that the argument is something that has an array-like form. And on the other hand, type reasoning itself requires tracking some logical relationships. For example, in this case, just determining what the type of x is going to be depends on what the value of the arguments.length expression is. So we see that there is now a circular dependency between the 2 kinds of analyses that complicates formal reasoning and potential implementations. And to convince ourselves that this is actually a problem that happens out there, we ran a study on the main TypeScript type definitions library called Definitely Typed. And one of the things we found is that in 25% of the files in there, about 25% of the functions are overloaded. And if we actually account for optional arguments as being a version of overloading, this percentage grows up to about 60%. So this is something that developers have in mind when they create their type interfaces. So how do we actually check overloaded functions? And we presented a solution to this in our paper last year at eCoop, and with our technique called two-phase typing. So I'll describe this briefly. Let's assume that we're starting with an overloaded function $reduce that we saw earlier of the body of this function, and assign one overload to each overload to each one of these clones, while keeping the bodies the same. So then what we do is we pick each clone independently, and we check them under its clone signature. So however, this part is a value and path insensitive type checking process. So we're going to inadvertently reach some errors due to value insensitivity. So at this point, instead of rejecting this program, we're going to be replacing the erroneous expressions with assertions for false. So basically, we're trusting that this is going to be indeed dead code. And moving on in the second phase, which is the refinement type checking, we can actually use a flow and path sensitive analysis to discharge these dead codes and actually prove that they're indeed dead code, and so the program is safe. So in order to scale to a reasonable part of TypeScript, we had to also take into account other type features that are there in TypeScript and enhance the support for arrays and have a more flexible object initialization. You can find details for this in the papers because I'm not going to go into them here. And what you can also find in the paper is some formal results of refinement type safety for a core language of TypeScript. So moving on, I'm going to give some info about how our experimental results were. And I'll start by describing our benchmark suite. So most of our benchmarks were taken from the Octane suite. In particular, we the Navier-Stokes, Play, Richards, and we also checked the transducers library, which is a JavaScript library for composable logarithmic transformations. The parts of the array manipulation module from the D3 JavaScript library, and parts of the TypeScript compiler. So the total tally for lines of code was about 2,500 lines. So now the annotation overhead to get these to check with our tool was roughly about 1 line of annotation for 5 lines of code. However, most of these annotations were actually used to providing TypeScript signatures, so the basic type signatures. And as a note here, our programs do need to be fully typed, so no gradual typing in the form of the dynamic type any in the signatures. 20% of the annotations were mutability related, and just the 17% was dedicated to value-based refinements. So with regards to the performance of our tool, most of our benchmarks were able to run in under 1 minute. An exception is the Navier-Stokes benchmark that has a big number of static array accesses, and these can be rather expensive for our SMT solver. So this is a list of the properties that we checked for. These include some standard properties of the form of a property accesses, array bounds checks, and overloads that we saw earlier. We also focus on proving that downcasts are safe, both ones that are based on class hierarchies, and also ones that are based on ad hoc type hierarchies created by the user. And we'll see in a second how this works. And also there were other user-specified values that we looked into. So to give a better idea of what we mean by safe downcasts for ad hoc type hierarchies, this is an example taken from the TypeScript compiler. And here we have an interface hierarchy, where at the top we have a type called iType. And as its children, we have types called iAny, iObject, and so on. So the problem here is that the runtime representation for TypeScript interfaces are plain JavaScript objects that don't really have any runtime information regarding the type that they had statically. So what the developers of this part of the code did was to explicitly create a field called flags to encode the type information. And they used that in various kinds of runtime checks that they needed to do later on. However, in doing so, they had several invariants in mind. In particular, if the value for this flags field masked with the hexadecimal value 400 is not 0, then this object is going to be implementing the interface iClass. And they had similar invariants in mind for the other parts of the hierarchy. However, the problem here is that these invariants were completely unchecked. So if we had, for example, the code on the top right, where we define a variable of type iType and then have a check on the value of its flag and then downcast it to an iClass. Now this code is probably correct because it adheres to the first part of the invariant. However, if we were to replace the check, the downcast from iClass to iAny, then we would still not get an error flagged, neither statically nor at runtime. But this is obviously something that we wouldn't want to have. So the solution that we came up with to check this statically was to use refinement types and encode invariants in them. So the key idea is that we encode type information in our logic. So assume we have an interface S. Saying that variable X has type S is equivalent to saying having the predicate implement X, comma S string, where S string is a textual representation for the interface S. So now we can assign a more precise type for the flags field called type flag inv. And then we want to have this type account for all the possible subinterfaces that can be encoded. So by using the same base type as earlier, the type flags, we can encode the invariants that we had earlier. Namely, if we mask the value of this field with the value 1, then we can get as a return that the containing object, this is why we use the reserved name this, actually implements the interface IAny. Then we can add similar cases for the rest of the types, and then and fill in the type for the type flags. So let's see how we can handle now the same example that with the downcast that we had earlier. So we want to prove the downcast to I class. We first use the fact that it implements the iType interface. And so therefore it enjoys the invariants that we have associated with the flags field. Then, since our analysis is path sensitive, we can encode the path condition, basically that masking flags with the value 400 is not equal to 0. And then we can leverage the second one of the invariants in the invariant list and deduce the fact that implements T I class. Finally, by using the original intuition of encoding type inclusion as predicates, we can reach the conclusion that T is actually of type I class, and therefore that the downcast is statically correct. So in conclusion, I presented refinement types for TypeScript, which was our attempt to an extensible static analysis for a modern scripting language. To get there, we faced several challenges, including variable reassignment, mutability, overloaded, and we try to keep the annotation overhead as low as possible. You can find the sources for our code, and including the source of the benchmarks, and also an online demo at the links in the bottom. Thank you.
Thanks, this is very cool. So the features that you have a lot in common with the dependent JavaScript system by Chug and some co-authors that you might know. But that had a pretty high burden in terms of annotation. Can you compare a little whether you needed the features, why you didn't need some of the more heavyweight features that system has, and how the annotation burden compares?
Right. So the main reason why our annotation burden is lower than in a system like that is that we use liquid types as a back engine. So we can have a lot of other predicates being inferred by that engine. So this is, I suppose, what was missing from an approach like DJS. In addition, there's a lot of other differences. One other very important one is that in DJS, you kind of had to reason about all the heaps that flew in and out of functions. We didn't want to have to impose this burden to the user. Certainly, this does restrict us in flexibility with respect to what kind of programs we can accept. So, because we can't necessarily enforce like the strong updates that you can encode in DJS. So yeah, in some sense, yeah, there are some programs that would inadvertently be checked with DJS and we wouldn't be able to handle.
I guess my question is, have you seen cases, does it just turn out that this is enough and we should all be happy?
Well, there are certainly cases that we can handle, and there is some a relevant paragraph in the paper that, for example, cases of flexible initialization are harder for a tool to handle. There are ways that we can overcome these if we use, for example, a more sophisticated system to track aliasing and mutability. We haven't explored these in practice, but the literature exists and they can be probably reused.
Have you investigated the use of refinement types for termination checking at all?
This has been done in other projects relevant to liquid types. It hasn't been done in our case.